Hello students, welcome to this session on solution to review assignment 4. Let us see the first problem. Assume the observation model yn is equal to xn plus vn, where vn is a zero mean white noise with variance 1 and xn has an autocorrelation function rxm is equal to 0.6 to the power mod of m, m belonging to z. This problem we considered earlier also. Find the transfer function of the causal IIR winner filter to estimate xn. So, we have to find out the transfer function of the causal IIR winner filter. Next, find the impulse response of the filter, and finally find the mean square estimation error. So, in this problem we have to find out the transfer function. Suppose Hz is the transfer function of the causal IIR winner filter. We have derived that Hz is equal to 1 by sigma v square Hcz into Sxyz divided by Hcz inverse and the causal part of this. So, this means this is the positive part, means causal part. So, what we have to find out is that first we have to find out Hcz. So, what is Hcz? This is the causal filter corresponding to spectral factorization of Syz. So, first we have to find out the causal filter corresponding to factorization of Syz. That means, we will write, suppose this is our xn, yn, this is the observed signal, and this is vn, where vn is a innovation sequence with variance sigma v square, and this one is Hcz. So, that way that observed stationary signal is considered as the output of a linear filter with input as the innovation sequence. So, that way we have to find out the expression for Hcz from the spectral factorization of Syz. Now, let us consider the parameters given. So, Rx of m is equal to 0.6 to the power mod of m. So, m belongs to set of integers. Now, Sx of z, power spectral density in z domain, generalized power spectral density is given by Rx of m into z to the power minus m, m going from minus infinity to plus infinity. So, this we can carry out the algebra, already we have done it. M is equal to minus infinity to infinity, Rx of m is equal to 0.6 to the power mod of m and z to the power minus m here. So, this we have shown that in earlier problem sheet we have already solved this, and this is given by 0.64 divided by 1 minus 0.6 z into 1 minus 0.6 z inverse. So, this is the power spectral density of xn. Then also we know that S xyz, because of this model, signal plus noise model, which are independent of each other, because of that Sxyz will be also equal to Sxz, that we have already established earlier. And Syz is equal to Sxz plus 1. 1 is the per spectral density of the white noise, because its variance is 1, and this expression we got as 2 minus 0.6 into z plus z inverse divided by this quantity 1 minus 0.6 z into 1 minus 0.6 z inverse. So, this is the Syz. Now, we have to do spectral factorization of Syz, spectral factorization of Syz, that is equal to 2 minus 0.6 into z plus z inverse divided by 1 minus 0.6 z into 1 minus 0.6 z inverse. Now, we are interested to factorize this in this form, sigma v square into 1 minus alpha z into 1 minus alpha z inverse divided by 1 minus 0.6 z into 1 minus 0.6 z inverse. Now, we have to choose this alpha and sigma v square in such a manner that corresponding filter will be minimum phase. In spectral factorization, whatever this causal part we will be getting, that should be minimum phase. So, we have this expression 2 minus 0.6 into z plus z inverse is equal to sigma v square into 1 minus alpha z into 1 minus alpha z inverse. Now, we can equating this expression and this expression, we will get sigma v square into 1 plus alpha square, that is the constant term, that must be equal to 2, and other part is sigma v square into alpha, sigma v square into alpha, that must be equal to 0.6. These are the equations we have to solve to find out sigma v square and alpha. Now, dividing this equation by this equation, we will get 1 plus alpha square divided by alpha is equal to 2 by 0.6, that is equal to 10 by 3. So, this is the relationship we get. So, from this alpha square minus 10 alpha plus 3 is equal to 0, which will give alpha is equal to 3 and alpha is equal to 1 by 3. For spectral factorization, because it should be that filter should be minimum phase, because of that we choose alpha is equal to 1/3. So, that way alpha is equal to 1/3 and corresponding sigma v square, from this expression we can get sigma v square is equal to 0.6 divided by 1/3, that is equal to 1.8. Therefore, this numerator part will be now that is sigma v square will be there 1.8 and then 1 minus 1/3 z into 1/3 1 minus 1/3 z inverse. So, therefore, Syz is equal to sigma v square is 1.8 8 into 1 minus 1/3 z into 1 minus 1/3 z inverse divided by this expression 1 minus 0.6 z into 1 minus 0.6 z inverse. Therefore, this spectral factorization theorem we can apply now, that causal filter will be given by, causal part is this 1 minus 1/3 z inverse divided by 1 minus 0.6 z inverse. So, that is the causal filter. So, that way this is my innovation sequence, and that is with variance sigma v square is equal to 1.8, and it is passed through the system, causal system, that is HCZ is equal to 1 minus 1/3 z inverse divided by 1 minus 0.6 z inverse, and output we will get yn. So, that way we do the spectral factorization. Now, we know that Hz, that is the transfer function of the causal IIR filter, transfer function of the causal IIR filter, and that is given by 1 by sigma v square into HCZ into the causal part of Sxyz divided by HCZ inverse. So, that way now we know HCZ is given by this, and Sxyz is equal to Sxz. So, Sxyz is equal to Sxz, and Sxz is given by 0.64 divided by 1 minus 0.6 z into 1 minus 0.6 z inverse. So, we know Sxyz. So, therefore, Sxyz by HC z inverse, that will be equal to 0.64 divided by 1 minus 0.6 z into 1 minus 0.6 z inverse. So, divided by HCZ inverse, HCZ is this, HCZ inverse will be 1 minus 1/3 of z divided by 1 minus 0.6 z, 1 minus 1/3 of z divided by 1 minus 0.6 z. So, we have to take the causal part of this. So, we have to take the causal part of this, So, this we can simplify, because 0.6, 1 minus 0.6 and 1 minus 0.6 will get cancelled. So, we will have this is equal to 0.64 divided by 1 minus 0.6 z inverse into 1 minus 1/3 of z. So, this is the expression for Sxyz divided by HCZ inverse, and we have to take the positive part or the causal part of this. So, we will find out the causal part. Now, we have to find out the causal part of 0.64 divided by 1 minus 0.6 z inverse into 1 minus 1/3 of z. So, positive part of this we have to consider, or causal part of this we have to consider. Now, this causal part will involve this, because this is the causal transfer function. So, that way this will be of this form, this will be equal to a by 1 minus 0.6 z inverse, and plus anti-causal part will be there. This is the causal part. So, this is causal part, because this part will involve the anti-causal part. Now, to find out A, we will multiply it by 1.6 z inverse here, this and this will get cancelled, and then we will substitute z is equal to 0.6. So, that way this will be A will be given by 0.64 divided by, here we will put z is equal to 0.6, 1 minus 1/3 into 0.6. So, this is the way we do the partial fraction expansion. So, using that we get this result, and this is equal to, this will be 0.8, because it will be 0.2, 1 minus 0.2 will be 0.8, and this will be 0.8. So, A is 0.8, therefore, our this causal part of this expression is equal to 0.8 divided by 1 minus 0.6 z inverse. So, therefore, Hz, that is the transfer function of the causal Wiener filter, causal IR Wiener filter, is given by that is 1 by sigma v square. Sigma v square already we have found out, sigma 1 by sigma v square into Hcz into Sxy z divided by Hc z inverse, that causal part of that. So, causal part we have already found out, this we have found out, sigma v square we have found out. So, that way this will be equal to 1 by 1.8, this is 1.8, Hcz is equal to 1 divided by Hcz is equal to 1 minus 1/3 of z inverse divided by 1 minus 0.6 z inverse into causal part of this is given by 0.8 divided by 1 minus 0.6 z inverse. So, this if we simplify, we will get this as 4 by 9 divided by, so this part will get cancelled, only we will have 1 minus 1/3 of z inverse. This is the transfer function of the causal Wiener filter. This is the transfer function of causal Wiener filter. Now, taking the inverse of this, so taking the inverse, we will get the impulse response. This is the causal IR Wiener filter, its impulse response Hn will be equal to, this is 4 by 9 into, this is 1/3 is there, into 1/3 to the power n greater than equal to 0. So, this is the impulse response of the causal IR Wiener filter. We have to also find out the minimum mean square error, MMSE, minimum mean square error, that is equal to, we have found out that actually this is equal to E of Xn minus that filter Hi y of n minus I going from 0 to infinity into, because error is orthogonal to data, there will be only x n will be here, and because of that it will be r x of 0 minus summation h I into r x y I going from 0 to infinity. And if we substitute this, if we substitute the values of r x 0, h I and r x y of I, we will get this will be equal to 1, r x 0 is 1 minus, now summation 4 by 9 is there, 1/3 to the power I, and r x y I is that is same as r x of I, that is equal to 0.6 to the power I going from 0 to infinity. So, this is the autocorrelation function. Cross correlation function is same as autocorrelation function. So, this is an infinite series, and if we carry out the summation, this is an infinite series and common ratio is less than 1. So, this will be simply first term, that is I is equal to 0, 4 by 9 divided by 1 minus common ratio is 1/3 into 0.6. So, that way this will be one minus 0.2, common ratio will be 0.2. So, that way we will get this, and this is equal to 1 minus 5 by 9, that is equal to 0.444. So, this is the minimum mean square error. So, this is the first problem. We will go to the next problem. First one is theoretical. Write down the expression for the normal equations and the corresponding minimum mean square prediction error for the pth order linear predictor. Suppose this is for a signal yn is the signal. So, that way y hat n is equal to summation h I into y n minus I going from 1 to p. This is the pth order linear predictor. Now, normal equation is obtained from the condition error is orthogonal to data. So, that way E of yn minus summation h I y n minus I going from 1 to p into y n minus j, that will be equal to 0, j is equal to 1, 2 up to p, because pth order linear prediction. So, p data are involved. So, from this we will get, we can write this expression first, summation h I into r y of j minus I, because n minus I minus n plus j. So, j minus I going from 1 to p, that must be equal to r y of j. So, this is the normal, j is equal to 1, 2 etc. up to p. So, this is the normal equations. So, there are p such normal equations, and then expression for mean square prediction error. So, m minimum mean square prediction error p e s p e is equal to E of y n, that is the data minus prediction h I y n minus I I going from 1 to P, this is the error, and there will be only yn term here, because this error is orthogonal to the remaining part of the error. So, that way this will be equal to ry0 minus summation hi ry I going from 1 to P. So, this is the expression for minimum mean square prediction error. Now, part B is this is part A. Part B, rym is equal to 0.5 to the power mod of m. So, that is m is equal to 0 plus minus 1 etc. Now, for first order linear predictor, for that what we will have? So, here P is 1, so there will be only one term. So, normal equation will be, what will be the normal equation? Normal equation will be, there will be only one term H1 into Ry, I going from 1 to P, P is 1, so that was one term only, 1 minus 1, that is Ry of 0 is equal to Ry of 1, implies that H1 is equal to Ry of 1 divided by Ry of 0. So, that will be equal to 0.5. We know Ry of 1 is equal to 0.5 and Ry of 0 is equal to 1. So, that way it is 0.5, H1 we have found out. Suppose this is first order prediction, so that way we will denote here 1. Okay. Now we will go to the second order predictor. Second order prediction is y hat n is equal to, let me call it as H2 of 1 into y n minus 1 plus H2 of 2 into y n minus 2. Now, we will have the normal equations H2 of 1 into r y of 0 plus H2 of 2 into ry of 1, that must be equal to ry of 1. This is one equation. Next equation will be H2 of 1 into ry of 1 plus H2 of 2 into ry of 0, that must be equal to ry of 2. So, this is the normal equations for second order case. So, here we can substitute the values. We have H2 of 1 into ry of 0 plus H2 of 2 into ry of 1 is equal to ry of 1, that is first term, first equation. Second equation will be H2 of 1 into ry of 1 plus H2 of 2 into ry of 0, that is equal to ry of 2. So, from this we will get H2 of 1, ry of 0 is 1 plus H2 of 2 into ry of 1 is equal to 0.5. So, that will be equal to ry of 1 is 0.5, and from second equation 0.5 into H2 of 1 into H2 of 2, that must be equal to ry of 2 is equal to 0.25. So, these two equation if we solve, we will get H2 of 2 is equal to 0 and H1 of 1 is equal to 0.5. So, this is the linear predictor filter coefficients for order 2. And we observe here that H2 of 2 is equal to 0, because from the data, this is the autocorrelation function of a first order air process. Therefore, if we predict second order terms will be equal to 0. So, that is expected. And we have to find out the MSP also, minimum mean square prediction error, that is for first order case. Suppose first order minimum mean square prediction error, that will be equal to RY 0 minus H11 into RY of 1, and this is equal to RY of 0, we have 1, and this is 0.5 into 0.5. So, that way it will be 0.75. And in the second case, this is first order, second order SPE is equal to again RY 0 minus H2 1 RY 1 minus H2 2 RY 2. Now, this is 0 and this is same as 0.5. So, that way this also equal to 0.75 only. Let us go to the third question. The autocorrelation functions of a WSS signal Yn at different lags are tabulated as below, and that is lag 0 it is 1, lag 1 it is 0.2353, lag 2 minus 0.6059, lag 3 minus 0.4071. So, apply Levinson-Darwin algorithm to find the first order and the second order linear predictors for the process. First part is that, and second part is find the reflection coefficient K3. For third order predictor, what is the reflection coefficient? Hence, comment about the model of the signal. We know the Levinson-Darwin recursion. This is the recursion. We have to first determine the reflection coefficient Km, that is given by summation Hm minus 1 I into Ry m minus I going from 0 to m minus 1 divided by minimum mean square prediction error of the m minus 1th order. These are the parameters of the m minus 1th order. So, from that we will determine the Km, that is the reflection coefficient of order m, and then for order m we will update the filter parameters by this equation. H of mi is equal to h m minus 1 I plus Km into h m minus 1 m minus I, and finally Hm will be equal to minus Km, Hm that is mth order last parameter will be minus Km, and mean square prediction error will be updated by this equation. We have to also initialize the algorithm. So, for that initialization that is Hm of 0 is equal to minus 1 for all m, that is one initialization, and epsilon 0 is equal to Ry of 0, because there is no prediction for 0th order predictor, and therefore, mean square error will be simply variance, that is Ry 0. Now, we have to find out, apply the Levinson-Darwin algorithm to find out the first order and the second order linear predictors. So, first order, suppose m is equal to 1, then K1 will be equal to, from this expression, h of, because it is up to m minus 1, m is equal to 1, it will be only one term will be there, I is equal to 0. So, that way h0 of 0 into ry m is equal to 1 minus 0 divided by mean square error, that is epsilon 0. So, that way h0 is equal to minus 1 into ry of 1 is equal to 0.2353 divided by epsilon 0, that is the same as ry 0, that is equal to 1. So, that is equal to minus 0.2353. So, here only one parameter is there, reflection parameter, and it will give us the corresponding linear predictor parameter, that is h1 of 1 will be equal to negative of this minus of k1, that is equal to 0.2353. Next we will go to m is equal to 2, and here we have to update the mean square error also before going to m is equal to 2. So, that way epsilon 1, that is the mean square prediction error, minimum mean square prediction error of the first order predictor, epsilon 1 is equal to epsilon 0 into 1 minus km is already we have found out, 1 minus 0.2353 square, and that will be equal to 0.9446. Now we will go to m is equal to 2. So, here k2 we have to determine, and if I put here m is equal to 2. So, it will be summation from I is equal to 0 to 1, then this term will be h1 of 0 and h1 of 1. So, that way first term will be h1 of 0 into ry of, this is 2 minus 0, ry of 2 plus h1 of 1 into ry of 1 divided by mean square error epsilon 1. And if we substitute the values, h1 0 we know, that is equal to minus 1, ry 2 is given, that is equal to ry 2 is equal to minus 0.6059 plus h1 of 1, that is equal to 0.2353 into ry of 1 also is equal to 0.2353 divided by E1 also we have found out 0.9446, and this will give us K2 is equal to 0.7. Therefore, we are interested in second order filter parameters. So, H2 of 2 will be equal to minus 0.7, and we have to find out also H1 of 1, H2 of 1, H2 of 1 will be equal to, from this, that is H1 of 1 plus K 2 into H1 of, that is 2 minus 1, and that is H1 of 1. So, this we can again substitute the values, and we will get this as 0.4. we know H1 of 1, K2 we know. So, therefore, it will be 0.4. So, we have found out the first order and second order linear predictor. Then finally, we have to find out the K3, and once we have these values H2 of 1, H2 of 2, we can find out the H2 of 2 is equal to minus 0.7 and H2 of 1 is equal to 0.4, and now we can update the mean square prediction error, that is mean square prediction error E of 2 will be equal to E of 1 into 1 minus epsilon 2 is equal to epsilon 1 into 1 minus K2 square. So, that will be epsilon 1, that is mean square prediction for first order predictor we know, and K2 we know. So, substituting we will get this will be equal to 0.4818. So, that way we have complete the two recursion in Levinson-Darwin algorithm to find out the first order and second order model. Now, let us go to find out K3. K3 is equal to summation S to I Ry 2 minus I going from 0 to 2 divided by epsilon 2 means minimum mean square error at iteration 2. Now, we have already values of this. So, this will be equal to, first one is I is equal to 0, H2 0 is minus 1, and Ry of 2, that is equal to minus 0.6059. Then second term will be H2 of 1, that is 0.04 into Ry of 1, that is 0.2353 minus H2 of 2, that is 0.7 minus 0.7, H2 of 2 is minus 0.7 into Ry of 2 minus 2 is 0, Ry of 0 is 1. So, this is divided by epsilon 2, that is the mean square prediction error at order 2, and this part now if we carry out the algebra, this will be equal to 0 by epsilon 2, that is equal to 0. So, K3 is equal to 0, and that is third order reflection coefficient is equal to 0. So, since K3 is equal to 0, that optimal linear predictor will be of order 2 only. So, that is our observation, that optimal linear predictor will be of order 2 only. We will not get any benefit by increasing the order, and this is why, because the corresponding model is a AR2 model. So, that is the advantage of this reflection coefficient. So, since it is an AR2 model, so after m is equal to 2, Km will become, after m is equal to 2, Km will become 0. So, this is the observation, that since it is an AR2 model, here after m is equal to 2, that is K3 is equal to 0, therefore, it will be an AR2 model, because for AR2 model after m is equal to 2, this reflection coefficient Km will be equal to 0. Thus, K3 is equal to 0. So, from this we can say that we can get the optimal linear predictor of order 2 only. By increasing the order, we do not improve the prediction. And secondly, this happens, K3 happens, K3 is equal to 0 happens when the corresponding model is AR2. So, for AR2 model, for m greater than 2, this reflection parameters will become 0. So, that is a test for AR2 model. So, if it is an AR2 process, K3 will be equal to 0. Similarly, if it is an ARP process, then Kp plus 1 will be equal to 0. So, K3 is equal to 0, it implies that we do not get any improvement by increasing the model order, linear prediction model order beyond 2, and this happens because corresponding signal model is AR2 signal, because for AR2 signal that Km will be equal to 0 for m greater than 2. So, for AR2 signal Km will be equal to 0 for m greater than 2. Similarly, for any suppose ARP signal Km will be equal to 0 for m greater than p. So, this is the importance of the reflection coefficients. Thank you.